If you came in late and want your quiz, let me know and I can hand it back to you after class. All right, so the last topic we're going to talk about for elimination chemistry is E1 chemistry. E1 chemistry, I'm sure you'll all be happy to know, is much, much easier than E2 chemistry. So let's go back and recall what occurs in E1 chemistry. We actually talked about it briefly at the start of the chapter. With E1 chemistry, we have a leaving group, just like with SN1, and what's the first step going to be? Leaving group falls off. In order for this to occur, this has to be a really, really good leaving group. The rate limiting step involves breaking this leaving group. So when this happens, you now have a tertiary carbocation. We know that tertiary carbocations are the most stable with the exception of what other carbocation? Resonance, right? So if we have resonance, that's even more stable, but tertiary is pretty great. All right, when we look at our carbocation, the carbocationic position is going to be called your alpha carbon. So I'll label that. And then one further away is going to be beta. It looks like all of our beta carbons are the same, right? So it doesn't really matter which one we work with, but we want to identify beta protons. So we've got 3 different ones. And the base, that we have around in solution doesn't even need to be a strong base because this intermediate species is so unstable. You can grab any one of these beta protons and clamp down. You end up with your leaving group. And then depending on your base, whether or not it's got a negative charge or not, it'll pick up that proton. So I'll just draw this as a covalent bond. Usually, though, your base is very, very weak. So let's make a note of that. What do you think happens if it's a really strong base? Yeah, E2 would be favored with the strong base. So we actually can't use a strong base in this situation because it'll outcompete the E1 reaction pathway and favor the E2 reaction pathway. So let's make a note of that. This is one of the key points, so I'm going to highlight it, that organic chemistry students forget all the time, is they think, hey, we started out with the tertiary substrate, shouldn't it do E1? No. You're thinking of SN1 chemistry. With E2 chemistry, if you have a strong base, we don't really care about the substrate so long as it has beta protons. Yeah?
Okay, 2 questions. Are we going to have to worry about any rearrangement?
Yes, absolutely. So the question is, do we have to worry about rearrangements? Yes. So just like with SN1 chemistry, anytime we can rearrange into a more stable carbocation, we will. So we do have to always watch out for that. The other thing that we said is true of E1 reactions as well as SN1 reactions. It is best if the leaving group is coming off something that is tertiary or resonance stabilized. Erase this. Or tertiary carbocation. You may still see it with secondary carbocations where it will rearrange into a tertiary, but the same idea applies, right? We want to rearrange into a stable carbocation. Yeah?
Does the size of the base matter for E1?
That's a good question. So the question was, does the size of the base matter for E1? No. In fact, we don't have to worry about Hofmann or Zaitsev products with E1 at all. The other thing students will ask is, you see when we're grabbing the beta proton there, does the beta proton need to be anticoplanar? Yeah, there's nothing to be anticoplanar with. That's a great point. So we don't have to worry about anticoplanar beta protons. We don't have to worry about the size of our base. We still might get a tiny bit of the Hofmann product, but Zaitsev product's always going to be favored for an E1 reaction, which is very nice. It simplifies just about everything. Yeah.
So if you were to just give us a reaction, how are we going to distinguish between the 4 if it's SN1, SN2, or E1 or E2?
That's a good point. So the question was, how can we distinguish between SN1, SN2, E1, E2? That's what we're going to talk about either later today or tomorrow, because there is a lot going on. As far as we're concerned right now, we're focusing on elimination chemistry, right? So how can we distinguish between E1 and E2 for elimination? Strength of the base. If we have a strong base, we'll favor E2. If we have a weak base, we'll favor E1, right? So right now, let's just focus on that because it is really overwhelming when you throw all 4 together. All right, let's make a note over here that we always favor the more substituted alkene Typically with these reactions, we don't even refer to them as Zaitsev and Hofmann. We only refer to Zaitsev or Hofmann for an E2 reaction. The other thing I like that you pointed out was that size does not matter. So you could have a large base, you could have a weak base. It doesn't do anything differently in this reaction. All right. All right, there is also one other thing to watch out for. And you guys actually saw this in lab, is if you have heat plus a primary or secondary alcohol plus a concentrated strong acid. So for example, in lab we use cyclohexanol and we use sulfuric acid and heat. We were actually able to do E1 elimination. And why is that? Yeah, exactly. We saw in lab, in this situation, the first step will always be protonation of your alcohol. So I'll just use sulfuric acid, which we saw in lab. We don't have a good leaving group right now, so just like with SN1 chemistry, we need to protonate this first. Once we protonate this, we've got a really, really good leaving group. At this point, our leaving group can fall off. This can give us a secondary carbocation. Is this going to rearrange at all? Nope, there's no way we can rearrange it into a more stable carbocation. And then at this point, your water is a really, really weak base. It can grab one of these protons, clamp down, whoop, give you your alkene, and then regenerate your acid. So when you look at this, the key thing is your strong acid, in this case, is usually catalytic. And what does it mean when it's catalytic? Yeah, it regenerates itself during the reaction. You can see we put acid in, but we kicked acid off in the end. So we don't need a full one-to-one stoichiometric equivalent. We only need a little bit in order for this to work. Why are we adding heat to this reaction? Because it's elimination and we want it to favor that over SN1 chemistry. And then we also need to have a primary or secondary alcohol because the carbocation that we're going through needs to be relatively stable. What do you think happens? Oh, sorry, this should be a tertiary or secondary alcohol. I got ahead on my notes. What happens if we have a primary alcohol? Do you think it's still going to be E1? Yeah, if we have a primary alcohol, it's thought to go through E2 rather than E1, and it takes a really high temperature, so it's not very common. Typically, you only see E1, and you typically only see dehydrations with tertiary or secondary alcohol, so you do need to watch out for that. Okay, so now what we need to do is practice a little bit. So let's do a couple practice problems. So let's do this one. And we're just going to use a catalytic acid, and rather than writing out full sulfuric acid, I'll just abbreviate it as H+. And then I'll write catalytic. And then the diamond signal down here, delta, means heat. So this is likely going to be an E1 elimination reaction. We know it's E1 because it's a secondary substrate. We've got catalytic acid and heat. So I'll give you guys a minute to do this, but I want you to determine which product or products you think you'll get from this reaction. I'll get us started too. I'll do the easy steps first. So first step we know will be protonation of our alcohol. And that's because the alcohol at first is not a good leaving group. Now we've converted it into a good leaving group. What should I do next? Kick off our leaving group. Okay. So we've got our carbocation. Does anybody want to help me with the next step? Rearrangement, right? Right now we've got a secondary carbocation. We know that that's not too stable. So are we going to do a hydride shift, a methyl shift? What do you guys think we should do? Hydride shift. And the reason being, we've got a hydrogen right next door, where if we move this entire hydrogen over to that carbocation, now we've got a tertiary carbocation, right? We know that that's energetically very favorable. All right, so now we've done the rearrangement. We now need to identify our beta protons. So I'm going to go ahead and draw in our beta protons using some blue arrows here. So I've got beta protons off of this methyl group. Got beta protons off of the other methyl group. Are those any different from one another? No, it doesn't really matter which of those we grab. We also have two beta protons coming off here. And if you remember, we kicked off water. So water is going to be floating around. Which beta proton do you guys want to go after first? Okay, so let's go after the ones on the right first. So when we do this, we can say, all right, we're going to end up with both methyl groups that were there in the same place. We've now got a double bond here, and we've got this right here. This is the most substituted alkene we can get, so this we immediately know will be our major product. Are there any other products you think we might get? Yeah, we could also go after one of these beta protons, clamp down. So we could say, hey, this could be a minor product as well. So we would get two different products out of this reaction. Do we have to worry about cis or trans isomers here? So for example, up here, is it possible to get both cis and trans? It'd be the same, right? So there's no point drawing it twice. You don't have to do that. Same thing with the bottom one. You can pluck protons off that top methyl group, but it gives you the exact same product. It doesn't really change anything here. So for this reaction, we get two different products. The top one we said would be major, bottom one would be minor. Is this reaction stereospecific, stereoselective, or regioselective? Yeah, so this reaction is regioselective. If you remember, regioselective reactions give you a mixture of products that are constitutional isomers where one is major and the other one's minor. So in this case, the major one we can see is the tri-substituted alkene. Does that make sense? You guys want to try a harder one? All right. This was one I got from the book. Depending on what edition you have, I think this is second edition, problem 81. And they say propose a mechanism and it looks pretty complicated, but it's not too bad. Got this bicyclic ring system. You've got an alcohol coming off that far end. you're going to treat this with catalytic acid and heat. And when all's said and done, you still have 2 rings, but the double bonds have moved around. And your final product looks like this. So let's try to draw a mechanism from how we can get from our starting material all the way to our product. I think this was actually an old exam problem. How many of you want to work on this as a class? Raise your hand. All right, so let's do this as a class. First step is going to be what? Protonation, just like we saw before. So kind of repetitive. Got a double bond here. Now we'll have a protonated alcohol, which is a great leaving group. Still have these methyl groups hanging off. What's the next step? Leaving group falls off. Okay, so we'll still have both ring systems. We've got a secondary carbocation right now. Is there any way to improve this? Yeah, in this case, we'd probably want to do a methyl shift, right? If we did a hydride shift from the bottom carbon, we'd just be going secondary to secondary. So let's take one of these methyl groups from the top corner and move it down. All right, so now we've got a secondary to a tertiary carbocation. Is there any way to rearrange this to an even more stable carbocation? What's better than tertiary? Resonance, right? So let's try rearranging it a bit until we get resonance. We know we've got this blue proton that's assumed to be coming off that top carbon. So when we move this over, whoops. Now we should have a tertiary carbon with resonance. In fact, let's draw both resonance structures out for this. And we know with resonance structures, you can move a pi bond over like that. Actually, sorry, I'm going to condense space here. Which would give us our double bond right there and our cation right there. So we know this is possible because this is tertiary with resonance. Does that make sense? All right. If we look at our final product, we're almost there. What do you think the last step's going to be? Yeah, we have to deprotonate a beta proton. We need to get a double bond right there. That means the beta protons we need to select must be coming off of this lower position here, right? Okay. Does it matter if they're anticoplanar or not? No, because it's an E1 elimination. So all we're going to do in this one is grab one of these beta protons, clamp down, and will give us our final product right there. So some of these are pretty tricky. You do have to pay very careful attention to resonance and rearrangement, things like that, similar to with SN1 chemistry. Does that make sense?